Okay, now let's take a look at rotational dynamics. So we know that sum of forces, the sum of net external forces, is equal to mass times a linear acceleration. And in rotational motion, what causes a rotational acceleration is a torque. So the sum of torques, the net torque acting on an object, is equal to, instead of it being the mass, it is the rotational inertia, and then instead of the linear acceleration, it is the angular acceleration. So this is for rotational dynamics, which will analyze rotational dynamics the same exact way that we analyzed linear dynamics. So in this question here, we have a propeller blade that can be modeled as a uniform bar, and then somebody hits it, and then we want to find out what the angular acceleration is of this bar. And so just like dynamics or linear dynamics, we want to start with drawing a picture of what's going on, a free body diagram of what's going on. And so put this in what we have given. And I'm going to draw a figure. I'll go ahead and establish a coordinate system here. This would be like positive x, positive y, and this is a positive torque and a positive omega and a positive alpha, right? And we have this propeller blade that maybe looks something like this, and it rotates around. But they say that it actually can be modeled as a thin uniform bar that's 2.5 meters long. So this is actually just equal to a bar that looks like this. That's 2.5 meters long. So 2.5 meters there, and it's free to rotate about a frictionless axis perpendicular to the bar. So there's it's penned right here, and it's allowed to rotate around, this way or this way, whatever. It's allowed to rotate around there, around its center, right? So that would be, at 1.25 meters from one end here. So this is like 1.25 meters. And we have a technician, and it has a mass of 24 kilograms. Maybe I should write that down here. Mass is 24 kilograms. A technician strikes it with a mallet 1.15 meters from the center with a 35 Newton force. So it's struck down like this. And it doesn't actually say which side. We'll just say it's over here, 35 newtons. And this is 1.15 meters away over here from the center. And we want to know what is the maximum angular acceleration it could achieve. And actually, the way I've drawn it here, it's going to be a clockwise, which is negative. But I mean, it could have just been hit over here as well, which would cause a positive, right? So let's just take the magnitude of it. I would say, we're looking for the largest magnitude of the angular acceleration, right? So when it's hit and it rotates around clockwise like this, it's going to rotate around the center, right? There's an axis that goes right through the center here, and it's going to rotate around it like that. And we want to know, what is this acceleration? So we know that it's the net torque which causes the mass to accelerate, right? And this mass has some rotational inertia associated with it here. And I'm just going to deal with the magnitudes, right? I'm going to deal, like I said, the magnitude of the torque and the magnitude of the acceleration. So I'm taking off the vector portion of this. Okay. We need to know a few things. We're looking for the acceleration, so we need to know what the torque is and what the rotational inertia is, right? So the torque is going to be, well, there's only the torque produced. Well, I guess if it's stuck right here, there could be a force right here, but let's take the sum of the torques around the center right there. So the sum of the torques around, let me call this the pivot P. So the sum of the torques around the pivot, this is the magnitude of this torque, is just going to be the 35 newtons times the moment arm, right? So we have here 35 newtons times 1.15 meters, and this is what? This is 40.25 Newton meters. So the torque produced by the technician hitting this is 40.25 Newton meters. And then we also need, obviously, our rotational inertia. And now we need to make sure to calculate the rotational inertia about the same axis that we're taking the sum of the torques around. This is important. That way, we're comparing, the same points, right? This is the torque causing rotation around point P, and this is the needs to be the inertia that is opposing rotation around the same point, around point P. And so this point P, this is the center, right? And if I look in that table of moments of inertia, the rotational inertia of a slender rod, a thin uniform bar, or a slender rod, about the center of it is 1/12 times the mass times the length squared. This is for a long, slender bar or rod about its center, or about axis through its center. You have to be careful here. If you were to take the rotation around this end instead, the rotational inertia is actually a lot more, because now you have more mass that is distributed a lot farther from the axis of rotation, right? So actually, if I were to take the rotational inertia around here, the rotational inertia around that point, call it L for the left end or something, this is actually equal to 1/3 ml squared. And this is, you can actually see this comes from, it's 4 times as much. This 1/3 is 4 times of 1/12, and you see on average all the mass is twice as far away, and then that's squared, so it's actually 4 times the inertia. So you have to be really careful that you're taking the rotational inertia around the same point that you are taking the sum of torques around, and vice versa. And so this is 1/12 ml squared. Then, and this L, by the way, this L is the total length. So this would be the 2.5 meters, right? And so plugging this in, the rotational inertia around the that center there, that pivot, is 1/12 of the mass, which was 24 kilograms, and the length was 2.5 meters, and this is squared, and so this comes out to 12.5 kilogram meters squared. And so then we have just to find the acceleration from this equation we had previously. Our acceleration is sum of torques divided by rotational inertia, and so the magnitude of it is the magnitude of the torque divided by our rotational inertia, and so this is 40.25 Newton meters divided by the 12.5 kilogram meters squared, and so then alpha comes out to 3.22 radians per second squared. So pretty much exactly the same way that we've looked at rotational dynamics, that we looked at linear dynamics, Newton's laws. Just have a little bit more here. We need to look at rotational inertia instead of linear inertia, so we need to look at a table and do a slight little side calculation for rotational inertia, and we need to do a slight little side calculation for torque. We think of that as like rotational force, but fundamentally it's still the same concepts there. Just a couple other small calculations on top of it.